so here's an example problem where we're going to integrate this square root of x squared plus z squared over a paraboloid. So specifically, it's the region bounded by x squared plus z squared equals y and y equals 4, which I've sketched out right here. Okay, so let's get down to brass tacks and figure out how to set up this integral. And let's see. So suppose I did what we've been doing for a while now and set this thing up first doing the dz integration as our first integral. All right, well then we can look at the top and bottom surface here. Let me grab them a little bit. So let's see, so we've got oops. Okay. So there's our top. And oh dear. There's our bottom. Okay. So let's make this one green and this one red in alignment with our usual color conventions. So this is the surface that our vertical line is going to exit the object through. And then we've got the this bottom part of the paraboloid, or paraboloidal shell, if you like, that's going to be where we first enter the object. All right, so I don't know about the shadowing here, but whatever, you get the idea. All right, so what's this going to look like then? Well, so I've just kind of separated it here to give the idea of like when we do, like integrate through some on one of these vertical lines, where do we first hit the object and then where do we leave it when we pass out to the top, right? And so let's see. So the upper boundary up here is going to come from z equals square root y minus x squared. And then the bottom boundary down here is going to come from minus root y minus x squared. And then after we're done with this integration, if we look at the projection downward, so once again you're up above it looking downward, then we're going to see this sort of parabolic shaped region like this that we would have to set up next, and we could have a let's see, if we were going to go in the dy direction here, we'd be going between y equals x squared and stopping when we exit through y equals 4. And so our integral would be, let's see, the triple integral over e of f dv is going to be, and we'll be going from minus 2 to 2, and then from x squared up to 4, and then from minus square root of y minus x squared up to positive square root of my y minus x squared. X squared plus z squared in the root radical, dz, dy, dx. And this, as you might have noticed, is horrible. You're not going to be able to integrate that. Okay, so we need to do something else. So the next idea of what to do would be to say, okay, let's take this guy again, and this time let's pull it apart and try doing the y integration first. So, and you know, probably anybody who's paying attention would have noticed that we've already got these solved for y equals this and y equals that. That might be a good hint that we should do the dy integration first. Now, in that case, the things we need here, for our top and bottom surface, we're going to be leaving through the sort of lid, and we're going to be starting over here with the bottom cup, or I'm not sure what you want to call it. Okay. And let me just color in our exit surface. Oop. Not good at staying inside the lines. Okay. All right. So that's what it looks like. So a horizontal line is going to puncture the object here and then leave exit wound right there. Okay. So let's see, what does this look like now? So now we've got the left boundary of y equals x squared over here, and then we've got the right boundary of y equals 4 over here. And then when we're done, the projection, so again, now you're way down on the y-axis looking this way, and what do you see? You see a circle. But not really a circle. You see an amoeba because I can't draw a circle. And then we can set up this in one way or the other. All right. So now the triple integral over e of f dv is going to be the double integral over the disk times the integral from the paraboloid y equals x squared plus z squared up to the plane y equals 4 of the integrand square root of x squared plus z squared, and then that's dy, and then we have dA set up over the disk afterwards. And so let's see, so if we do that first integral, there's no y in that radical, so we can pull it out in front of that integral, and 1 gets integrated up to y, which is then evaluated from x squared plus z squared up to 4. And then we have, let's see, so this is going to be the double integral over the disk of x squared plus z squared, and then we've got 4 minus x squared plus z squared. And about at this point, you're thinking, gosh, that looks exactly like the kind of thing that I would like to use polar coordinates for, because that would make it so much simpler. And the only problem is polar coordinates are for x equals r cosine theta and y equals r sine theta, and it doesn't say anything about z. And then you say, ha! I am a student of math and not a mere mortal bound by these limitations. Let's just do it for z instead. All right, fine. So then this is going to be 0 to 2 pi, 0 to the radius of our disk is 2. And then we've got r times 4 minus r squared. And then we've got r dr d theta for our area element in this setup. And notice that the Jacobian comes through exactly the same as it did for when we were using x and y. If you want to go through the procedure, you can check me on that, but it'll work out, I promise you. And then this can be readily integrated and you get some answer, and it turns out to be this 128 over 15 pi, which, lovely, right? I'm sure that you were waiting with bated breath for that answer. This idea right here is called cylindrical coordinates. So cylindrical coordinates is a way of setting up a triple integral as polar for 2 dimensions plus 1 Cartesian going in the other dimension. So sometimes you'll have polar in the xy plane and then the Cartesian will be your z, or maybe like we had right here, the polar was in the xz plane and the Cartesian was the y direction. Doesn't matter which one. So we'll talk more about cylindrical coordinates in forthcoming chapters.